So I'm presenting some joint work with Del-Pinto and Renate Schmidt from the University of Manchester, as well as Sophie Tourret from the Max Planck Institut Informatik. And I'm Koopmann from the TU Dresden, and the topic of my talk, as already introduced, is on signature-based abduction for expressive description logics. So let's start with a quick reminder of what abduction actually is. So the basic idea is very simple. You have some knowledge K and an observation psi that does not logically follow from your knowledge base, and you're looking for an explanation of this observation, also often called hypothesis. And here the idea is that extending the knowledge with the explanation would logically entail the observation. So like this, the definition is highly incomplete. Usually you have more requirements, as otherwise the problem is quite trivial. And there's different use cases why abduction is interesting. The classical one is in diagnosis. So your observation might, for example, be a description of symptoms of some patient, and you would like to have as explanation some theory about a disease he might have that would explain these observations. Another use case, especially in the area of description logics, is explaining why something does not logically follow and finding a solution on how to fix this problem. So let's make this a bit more explicit and also motivate the specific type of abduction that we worked on. So what we see here is an ALC knowledge base that says that an Ebola patient is a patient with a disease Ebola, that someone that was in contact with an Ebola bat becomes an Ebola patient, and that everyone infected by an Ebola patient also is an Ebola patient. Finally, we have some so-called A-box information talking about a specific object patient that is an Ebola patient. Now, the observation we would like to explain is that patient 2 is an Ebola patient. And if we do not constrain the problem any further, a possible explanation would be, well, patient 2 is a patient that has Ebola. But that does not really explain anything. But purely logically, it is hard to find out what actually the explanation is we're looking for. And one could argue that the problem as such is underspecified, and we additionally should give a vocabulary of abdusables that restricts the space of explanations to those that are actually diagnoses. And in this case, we get more useful explanations as we would expect. For example, patient 2 was in contact with the Ebola bat, or he was infected by patient 1. So let's make this formal. I'm looking here at the description logic ALC, and an abduction problem here is a triple of this ALC knowledge base K, an ALC knowledge base psi, the observation, and a set of abdusables. And we're looking for an explanation that satisfies these three conditions. First, it is consistent with the background knowledge. Second, it entails the observation. And third, it only uses the abdusables in the language, which can be combined in any way allowed by the logic. Finally, we would like to find all possible explanations, and we would like to cover them in a compact way. And this is why we also define an optimality criterion. And we say that for every ALC knowledge base that satisfies these three conditions, it should be covered in the sense that this hypothesis would be more specific. So we would like to find an explanation that covers all possible explanations in the signature. So as people who are familiar with the description logic might have already figured out, we can't do that in ALC alone. We need a more expressive logic. So first of all, we need to be able to express alternatives. So as we saw before, it could be that there's two different ways in which the observation can be explained. And for that, we need disjunction of knowledge bases. Second, it could be that there are unknown individuals that play a role in explaining the observation. For example, there could be a third patient that explains why the patient 2 has Ebola. And to encounter this, we have to extend the description logic further with inverse rules and nominals. And finally, we can think about any unbounded sequence of patients as well. And this can only be covered by a finite formula in description logics if we have least fixed point constructs. This would actually be an optimal explanation for our example. So in general, the shape of the explanations is a disjunction of knowledge bases, and we can see this as a disjunction of alternative explanations. This is optimal if all explanations are covered, but it could still be that the shape is not optimal because there are logical dependencies between those explanations. And this is why we define the space of independent explanations. And intuitively, the idea here is that you remove redundant knowledge bases that would entail the remaining disjunction. And computing this can be done if we have a method for computing optimal explanations, because then we just have to filter out the redundant disjuncts using entailment tests. So how did we solve this problem? So it turns out that this variant of abduction that we defined is strongly related to another problem in AI called forgetting. And while in abduction, we're looking for a weak knowledge base that entails something, here in forgetting, we're looking for the strongest entailed knowledge base within the signature. So we turn around the direction, and this can be exploited using negation. So we can compute, in theory, an optimal explanation as follows. We start with a knowledge base combined with the negated observation. We perform inferences on the names that are non-abusable, and then we obtain something from which the hypothesis can be extracted. And indeed, there are methods for forgetting in various description logic, including ALC knowledge bases, but there are some problems. First, they do not have the expressivity to express something like that. And second, they behave relatively bad in practice if we want to deal with arbitrary inputs, which is why we have to think about some optimizations if we want to be able to solve this problem practically. So our approach was to use a resolution-based forgetting for ALC and extend it to the setting. And second, to make it practical, to come up with a reasoning procedure that focuses inferences on the negated observation and ignores the knowledge as much as possible. The method we're using, I'm just giving a high-level perspective. One of the core ideas is to use a specific normal form that gives us a termination, because only finitely many things can expressed. And this normal form mixes description logic with first-order logic constructs. And the way the method works in general is that we first classify the input and compute inferences on the non-abusables as denoted before. And this way we can stepwise eliminate or forget these occurrences, resulting in a new class set that we can then declassify back into the description logic that we want to express the solution in. So some additional things had to be done to make this work. So first, as already said, the original forgetting procedure is not able to perform in this extended logic, and extending it had some surprising challenges. So we had to add some additional rules, and this was mostly challenging from an implementation point of view. Second, the denormalization step that I talked about before to get from the clausal form back into a description logic turned out to be very different to the previous approach. And in fact, it is in this denormalization process that all the operators I discussed before, like nominals, inverses, and fixed points, are introduced. So in the previous forgetting methods, this was usually a very simple step, and now there's actually some more reasoning involved, so that we actually needed a new set of rules to do it. And finally, how did we focus inferences in the way I described? We used here something that is not new in the area of KR and reasoning, the so-called set of support strategy, a modified version of that. So the idea here is to separate the set of clauses into two sets, a set of background clauses, a set of support clauses, and have the side condition that inferences should always involve at least one support clause. And so far so simple. Unfortunately, like that, it does not work with our specific calculus. We had to do a bit more. And the main reason is that there are dependencies between clauses that require us to move clauses from the background set to the support set. And this introduced some additional termination problems. The details of that you can find in the paper. And yeah, we implemented this system in Java using standard libraries out there and evaluated it on a set of realistic ontologies. So here we use the ontologies from the owl reasoner competition from 2015 because it's a well-balanced set of ontologies. We randomly generated small observations in 4 different sets. I'm not going too much into detail here. Maybe the, in my point of view, interesting thing here is that we generated names of abdusables by randomly picking about half of the names that occur in the ontology. And that is interesting because resolution-based abduction and resolution-based forgetting, the method that we started from, would always fail with these kind of signatures because it would be too challenging. These methods usually work well with either close to 0 or close to 100% of names. So this is a stress test for the set of support strategy. And we used a quite normal work PC for evaluating the experiments. So let's first look at the computation times. So the set of support strategy helped. We were able to compute solutions within the time window in around 90% of cases, up to 96% depending on the observations. And the running times were usually in the range of seconds, even though we came also close to the timeouts. So we see here the optimal explanation and here the space of independent explanations that is obtained after removing redundancies. Actually, what is displayed here is the additional step of removing redundancies. Second, what is the shape of the explanations we observed? So first,
Patrick?
Yeah, I have 2 minutes left.
1 to 2 minutes, yes.
1 to 2 minutes, depending on how many questions. So I hurry up, sorry. So since we randomly generated both signatures and observations, in a lot of cases, there was just no explanation, not because our method is limited, but there is just no explanation possible within the signature. This was the case in 2/3 of the cases. And in the remaining cases, the sizes of the explanations were usually similar to the observation size. But in extreme cases, they could be very large. And something similar was observed if we look at the disjunctions, at the alternative explanations in the space of explanations. Usually these were small, but they could get very large. And here it turned out that a lot of redundancies could still be detected. So that actually often the number of alternatives was relatively low. And with that, I reached the end of my talk. Just a quick recap. So we presented a method for signature-based abduction, which was before only looked at in limited description logics or with a limited setting. Used something based on resolution and evaluated and implemented it. And currently we are looking at the problem from a theoretical perspective, trying to understand the complexity better, as well as how it behaves with different description logics and minimality criteria. And with that, I would like to end. Thank you very much.